we got this one. How do you solve this? Yep. So if u is r squared plus y squared, du is 2y dy, and so 1/2 du equals y dy. So that gets thrown into it, and so I get j hat k lambda over 2 integral of du over u to the 3/2 from 4 to or ignore the new limits of integration, just solve it as you normally would, and then substitute the value in for u, or the expression for u, and then plug 0 and 4 in. That cancels out with that, and get a minus sign there. That is that. So plus j hat k lambda times 1 over the square root of 20 minus 1 over the square root of 4. Any cause for people to correct any mistakes they made or ask questions?
Wouldn't it become minus?
Oh, yes it is. There's something that's off there. Wait a second. Oh. Why didn't you correct this? Theta, I've defined theta here. And it is an angle that is is between 0 and 90 degrees. So sine theta is going to be a positive number. Except from the context, I know that the electric field is going to be down, so there really should be a negative there, 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 and then that negative is going to cancel out with that negative. There. Yeah, okay, that works.
Why'd you put negatives over there?
Say it again?
Why'd you put negatives over there?
Because I know the electric field's gonna be going into the fourth quadrant.
Okay.
Given my definition here, I know it's gonna be in the negative j hat direction. Sine of theta, the way I've defined theta here, sine of theta will be a positive number. So I have to put in the negative sign to account for the fact that it will be going down.
Basically, if you had, like if you had 180 minus theta or something, it would give you the same negatives, I think.
Yeah.
Yeah.
Yep.
Theta's going off that way as opposed to, it's like almost like you're shifting the
Yeah.
coordinate plane over.
So if I had made this 180 minus theta, and that 180 degrees minus theta, actually,
hundred fifty degrees if theta was 3.
No, oh, no, not 180 minus theta. It would be that actually, if that's theta right there, this angle right here would be negative theta. So it would be cosine, technically it's cosine of negative theta and sine of negative theta.
Oh, because you're looking at the others, okay.
So cosine's an even function, so that's the same as cosine of theta. Sine's an odd function, so you get negative sine of theta. Or, I know the answer is gonna be in the fourth quadrant, so whatever I get over there, I'll get two numbers and then I'll go, oh, that's supposed to be negative. Not the best way of doing it, but as long as you haven't made any other careless errors, it works. All right, so we are now left with I hat 9 times 10 to the 9th. Lambda is Q over L, so it is 3 times 10 to the negative 9th divided by 4. That's lambda. R is 2. And this becomes 4 over square root of 20. Plus j hat, 9 times 10 to the 9th. Times the linear charge density, 3 times 10 to the negative 9th over 4, times whatever radical 20 minus 1/2. This is negative, which is what we would expect, because we do expect a negative j hat.
So you have an electric field coming from dq, is that what's going on?
That's how we started.
Okay, and so it's going out that way, so if you had the opposite field, it would be going towards dq, and then you would use the other theta?
Technically, I could still do the exact same thing. If this were negative 3 nanocoulombs, if I just plugged in negative 3 at this point, then the signs would have ended up correctly. Then it would have been a second quadrant.
Oh, okay. Everything's the same, you just change the charge.
Yes. So in the master set problem from the next chapter, I think it's the next chapter. Unless it's stated otherwise, it's actually easier just to assume it's a positive charge, and then if it ends up being a negative charge, the math will still work out.
Did you say where the, 3 times 10 to the negative 9 over 4, where did that over 4 come from?
This is the linear charge density lambda. The linear charge density, it's a uniform charge density, so I could look at any small segment, or looking at the whole segment, I gave it the total charge and the total length. So it's, linear charge density is the total charge over the total length.
So why was it 2 in the first one, and then 4 in the second one?
Why is it, it's over 4 here, over 4 here. That too comes from the fact that you're dividing by big R.
Brian, so is that the final form of this equation?
You would use a calculator to
Okay.
come out with it, and don't forget units.
Yeah.
What will the units be?
Wait, no,
Newtons per coulomb.
Yeah, newtons over coulomb, or coulomb. Questions to here?
Newtons over coulomb, force per coulomb, basically.
Yeah, force per charge.
Force per charge. What exactly does that mean?
If I have an electric field of 5 newtons per coulomb, that means for every coulomb that I stick into it, I get 5 newtons of force.
Okay, gotcha.
Yeah, it would be whatever that is I hat plus whatever that is J hat.
So then, I'm not saying, but, you would put it in like whatever A hat is, like newtons per coulomb, and then the I hat.
Oh, so let's just say, I'll make up a number here, let's just say this ends up being 4, and this ends up being 7. Then I would write the final answer as 2 ways to do it, 4 newtons per coulomb I hat, actually that should be negative, minus 7 newtons per coulomb J hat. That's perfectly acceptable as the answer, assuming 4 and negative 7 are correct. Or I could write it as 4 I hat minus 7 J hat, parentheses around the whole thing, newtons per coulomb. If you only want to write the units once, don't forget the parentheses.
And then if you wanted magnitude, we'd have to put that back into just one number.
If I ask for the electric field strength, then you would use Pythagorean theorem and figure out what the magnitude is.
Okay, so we could write it for the string
Yeah, the strength,
is
the electric field strength is just the magnitude.
Okay. I got,
We have legitimate answers now?
I don't know, but I got 27 and square root of 5 over 20 for I hat. And then,
Like that?
and then for J hat, I got negative 1.865651. Sorry,
Is there a reason you didn't just, you're
oh,
using
my
the calculators?
Yeah, this calculator, it does, like, it doesn't do,
Oh.
it doesn't. But I can convert it.
Oh,
It's a 3.01869. Oh, 86. Okay, 3.01869. And then so on and so forth. That's what.
We're not gonna do anything else with this number, so if they're off, then people can correct it. But I have been in classes where I made a careless error in a calculation early on, get to the other end of the board, realize my answer can't be correct, and someone said, oh, you made a mistake back there. So you need to catch my mistakes. The nicer things will be.
I got the second one, but I'm doing a different first one.
Yep. What you get for the first one?
Yeah, like a 60.37,
You got 60 something?
yeah. I may be wrong too, but that's what I got for the first one.
No, I got the same as the 3.019.
Really?
Yeah.
Okay, so it's,
Yeah, and that's what I got for the second one too, the negative 1.86, yeah.
But I'm pretty wrong. I was so scared. I'm like, I didn't just
Oh, it's
embarrass
negative.
myself.
Okay. Alright, so we've gone through how to calculate electric field. There, obviously, we can make this more complicated. I don't feel a need to make it more complicated at the moment, but there are masters that problem will be more complicated. But I believe in you. You can do it. Or
More
ask
complicated
questions.
than this one.
Pardon?
More complicated than this one.
Yeah.
But this is like a cakewalk compared to the master set.
No, I mean, the trouble is that if I made the electric, if this charge distribution went down there, we'll still make it 4 meters. I mean, there, if it's below that point right there, some students get messed up because they're not defining variables properly. if y is defined as where it is relative to this right here, right? Then no, actually, if you define y to be from the bottom, this is where they mess up. If you define y to be from the bottom, then the limits of y, the limits of integration are not actually gonna be from 0 to. All right, why don't we take a look at a more complicated version of it?
Well, they are if you move, or if you change R too, right?
Yeah, you need to take into account the fact that if I gave you that this is the point 2, 0, that we're starting below 0, and so let's see, you do y from here, this would go from say -1 to -3. There we go. Because I had students choosing y to be 0 here, but doing limits of integration from -1 to 3, type of thing.
Well, you could do 0 to whatever then, right?
You could do 0 to 4, yeah, you could shift the axis.
But then you would have a larger R too? Does the triangle will get bigger?
A larger or little r?
Larger, big R?
It's
Well,
still 2
and a
meters
larger
away.
weight. Oh, okay. Right.
But it's that mixture of defining from the bottom, the variable, your sort of new variable, but doing limits of integration based on the coordinate system. That's where students have messed up.
Would you also have, electric field coming at different angles then? Below and above, or?
Yeah. But that would be taken into account, you take that into, that should just work out in the math. Because this distance right here would be y minus, if you're, depends on where you're defining y. If you're defining y from here, this would be y minus 1, would be that distance. Because if you're here, where you define y to be 0, you would be at -1, so that distance would be -1, yeah. So as long as you define that properly, it would take into account the fact that you'd have some below the axis here, or some of the electric field going into the first quadrant.
But then you still take the limits of integration from -1 to 3, or from 0?
You take it from,
We're mixing and matching here.
if you were to set y at -1, you'd have to take it from 0 to 4, because you're
Yes.
setting y as 0. But if you were to keep it as -1 to 3 and set y on the origin, then you'd have to take it as -1 to 3 for your
Yeah,
integral.
and then this would just be y.
Okay. That mostly makes sense.
Because when you plug in y is 0, it'll come out to -1 when you have y minus 1. And then once you plug into 4, it'll come out to 3. It's basically the exact same thing, just
Yeah.
Trouble comes when you mix and match.
Why does the angle of this work out though?
Because if your limits of integration are going from, so if you choose the regular axis here, and y is coming from the normal, from 0 there, when you get the -1,
Oh, that's what does
Yeah.
takes it into account, yeah. It's the limits of integration that does it,
yes.
okay. And that works because there's a uniform charge density. So it's like coming the same from all directions, basically, no matter where the DQ is.
Coming the same from all directions, that,
No?
because it is a uniform charge density, we can, I feel like that question is very wide and broad. Yeah, ask that one again.
Well, DQ, we're getting the field from DQ, and DQ is theoretically any point between those limits of integration, right?
Right.
And that, but at any point, it's going to be the same electric field, because it's uniform charge density.
It's not the same electric field because little r is gonna vary. The distance between this and that are gonna be the same. The formula is still the same, just that little r is a variable here. That's where I was hesitant, because it's the same in terms of the general generic equation here. It's not the same in terms of magnitude, because the electric field from this DQ would be the biggest one, because it's the closest. I should say the magnitude would be the biggest. That would be the smallest, because it's
The
farthest away.
DQ is the source.
Yeah,
I thought the source, it all depended on the source, and the electric field was the same, no matter where this, like. So what P experiences is gonna be different, but the electric field from the source is always the same. I think that's probably.
that's the part if I have a line of charge here, uniform charge, linear charge distribution. If I take some DQ there and some DQ here, the electric field at that point would be the same magnitude as the electric field at that point, sorry. The electric field from this point, from that DQ, would be the same as the electric field at that point from this DQ. However, the electric field at this point is stronger here than it is from here. So when you say the same electric field, in my mind, I'm thinking magnitude and direction, and those are, but different than any single point.
Like you have to have that point for that statement to mean anything, like how strong it is.
Yeah, P is very specifically at this point right here. I can't just say I have a uniform line of charge here, what's the electric field? That is just way too open-ended, because the question is where. Infinite distance away,